Pairwise dedup is not enough when duplicate documents form clusters. We'll use MinHash LSH and graph components to pick the canonical result. This is the pattern you'll be able to implement by the end, which groups near duplicate documents and chooses a single canonical version per cluster. I'm Professor Pi, teaching search and IR with simple Python. Web crawls and scraped feeds create lots of near duplicates. A single pairwise dedup step will remove exact copies, but it misses clusters. Imagine several rewrites of the same press release, or many pages that share large overlapping paragraphs. Success here means grouping those near duplicates together and keeping only one representative for each group. That cleans indexes, saves storage, and improves search quality. At a high level, we need 3 ideas. First, a way to compare documents by their overlapping content without heavy token-by-token work. Second, a fast index that brings likely pairs together without quadratic comparisons. Third, a small graph step that turns those candidate edges into clusters and picks one canonical item per cluster. The method trades a bit of approximation for big speed gains on medium to large collections. We will build a tiny pipeline on a few toy documents. It will show exact bigram Jaccard as a baseline. Then, we will create compact MinHash signatures to approximate Jaccard. Next, we will insert signatures into an LSH index to pull candidate neighbors. Then, we will connect neighbors into components and pick a canonical document per component by exact Jaccard within the cluster. This keeps the expensive exact checks local and efficient. Next, we'll compute a simple exact similarity baseline. This snippet computes token bigram Jaccard to spot the most similar pair. We create a small list of short documents in the variable docs. The tiny function sh builds sets of word bigrams, which capture local phrase overlap without needing external libraries. A list comprehension evaluates Jaccard similarity across all document pairs using set intersection and union. The max call selects the highest similarity pair, returning both the indices and the score. Increasing the shingle size k makes matches stricter and reduces false positives. Decreasing k makes matching looser and finds more pairs. The printed pair and Jaccard score show the closest near duplicate under this basic exact set method. Now we'll build compact signatures that approximate set overlap. This example creates Datasketch MinHash signatures to approximate Jaccard similarity efficiently. The variable numPerm controls the number of hash permutations, and seed ensures deterministic signatures. For each document in docs, we update a MinHash with its bigram shingles from SH using encoded strings as inputs. We then compute an estimated Jaccard for the closest pair found earlier with msigs.Jaccard msigsj. Larger numPerm yields tighter estimates but costs more memory and time. Smaller values are faster but noisier. The printed estimate shows how closely MinHash tracks the exact Jaccard for that specific pair. Next, we'll use LSH to find likely neighbors quickly. This code indexes MinHash signatures in a Datasketch MinHash LSH to retrieve near duplicate candidates. The LSH object is initialized with a similarity threshold and the same numPerm used to build signatures. We insert each signature keyed by its document index string, then query with the signature of a chosen document keyd. The call lsh.query returns candidate keys that are likely above the threshold, which we convert to integers and sort for stable output. Raising the threshold reduces candidates and false positives. Lowering it expands recall, but may add noise. The printed list shows which documents the LSH believes are near duplicates of the query. Now we'll convert those candidate edges into connected clusters. This snippet turns LSH collisions into clusters using a compact union find. We maintain a parent list P and a find function F for component roots. For each document signature, LSH.query returns likely neighbors. We union indices when they co-occur, merging them into the same component. After processing all signatures, a pass over all indices groups items by their root into the dictionary G, then sorts clusters by size and index. Tighter LSH thresholds earlier produce fewer, cleaner edges. Looser thresholds make components larger, but risk mixing topics. The printed cluster count and the largest cluster show how near duplicates have been grouped. Finally, we'll pick one canonical document from each cluster. This example selects a canonical document for each cluster by maximizing intra-cluster Jaccard similarity. The list groups contains connected components from LSH. For singletons, we keep them as is. For multi-document clusters, we compute a score per candidate as the sum of exact Jaccard values against all other members. Then choose the index with the highest score. Using exact Jaccard here sharpens selection, while LSH already cut the candidate space, keeping the overall process efficient. Preferring the highest scoring item tends to keep the most representative content, which prevents redundant results. The printed canonical IDs and drop count show how many items will remain indexed for cleaner search. In a real pipeline, the toy corpus maps directly to a document shard. MinHash plus LSH cuts candidate growth, so exact Jaccard runs only inside clusters. That keeps CPU low while preserving high quality for final selection. On larger sets, you would batch signatures and tune thresholds to match desired recall. Recap: it groups near duplicates using approximate MinHash signatures and an LSH index. Use it when you need to deduplicate noisy or rewritten content at scale without quadratic cost. Caveat: approximation can merge near topics if thresholds or shingle sizes are too loose. Next step: tune the LSH similarity threshold to trade recall for precision and measure cluster quality on your dataset. If short, practical IR helps, subscribe and watch the IR videos.